Physics in 24 Questions, Halliday Resnick and Walker, 9th edition, Fundamentals of Physics. So what I'm doing, if you haven't seen this, playlist for the whole thing's down below, is I'm picking 24 questions and I'm solving 24 problems as a way to kind of give a review of the course. Not teaching everything because I can't do everything in a short amount of time. And it's, I'll be honest, trying to pick that one question. It's like, oh, I want to do this question too. I want to do this question. I'm trying to do one question. And it's not for every chapter. I didn't do chapter 1. I thought it was kind of dumb. Well, it wasn't dumb. It was kind of dumb. But, okay, well, let's just get to it. I'm in chapter 9. And I'm doing the following question. I skipped this last time. I got to do the question first. So here's the question. A bowling ball is moving along and it collides with an identical mass stationary ball, and then they deflect off at different angles. And so if the initial velocity of this is 2.2 meters per second, and then the final velocity for ball 2, that one right there, it doesn't really matter, is 1.1 meters per second at a 60-degree angle right there, what's the final velocity and magnitude and direction for the other ball? And is it an elastic collision? I think that's a pretty good problem that kind of encapsulates, summarizes most of the things. So chapter 9 is kind of weird. It's about center of mass and linear momentum. I'm going to talk briefly about center of mass, linear momentum, and collisions, and then we'll do the problem. That's how it works here, right? That's how we do things. So let's talk about the center of mass. I'm not really fond of this right now, but if you'll notice before we looked at things like this, oh, here's a force pushing on this and maybe it moves in some particular way, and we treated the objects as point masses. Now, when we did work energy, there were some weird things about how far does the center of mass move compared to how far the force is applied. And so that did cause an issue, but they didn't really talk about the center of mass. That's fine, you can't do everything right away. But it's possible that you could have an object with individual pieces, M1, M2, M3, M4, and this moves as a rigid object through space. If we want to use Newton's second law, F net is mass times acceleration. This is actually the acceleration of the center of mass. And, there's some other things that can happen too, right? Because the thing could rotate also, but we're not doing rotation just yet. So we do have to find this value of the center mass, which was what we would plot the motion of that thing as it moves through the air or however it moves. I like to define center mass based on torque, but that's actually the center of gravity. But let's just define it. So suppose I have a bunch of points. I'm going to give them point, 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 and they all have mass, and they all have position. So this is Ri, that's the vector position of the mass, Mi. So they all have those things. We can define the center of mass vector as the sum over I, Ri vector, Mi, divided by, I'll just write this as M total, divided by the total mass. So you take each mass, you multiply it by its vector position, it's still a vector, you add up all those vectors, and then you divide by the total mass. If you've ever calculated your grade in a course, the weighted grade, it's the same thing. Okay, so that's how you would find the center of mass, and then we can use that, well, we don't really use that, but we're not going to do a center mass problem. The other thing in here is momentum, and the momentum principle really is in here. So we define momentum as mass times velocity. So it is indeed a vector. And with that, we get, I'm going to go ahead and write the momentum principle. The momentum principle says F net on an object is dp dt. Or if the things are constant, you could write that as delta p delta t. So this is a way to say momentum, or a net force on an object, changes the momentum. And that's one way to think about Newton's second law. And this is the same thing as Newton's second law, right? Because if I put in mv for p, I get F net is d mv dt. Well, if the mass is constant, I can pull that out front, and I get m dv dt, or m a. Because remember, the acceleration is dv dt. So it's the same thing. Then why do we do it? Well, it's actually not always the same thing. There are some cases where you could have the mass change, and then this wouldn't work. So they talk about rockets and the rocket equation. I don't want to talk about that too much, but you know that if you have a rocket and the rocket's accelerating and using its fuel, well, the mass of the rocket decreases, so the mass is not constant. This comes also, we can use this definition to derive impulse. Impulse, they use the vector j, and it's the integral over time, t1 to t2 of f dt, right? Because the net force, that's right? It is f dt, yeah. And this is going to be equal to the change in momentum. So the impulse is the change in momentum of an object. If forces are constant or the time interval is short, you can write this as dp equals f delta t, and that way it's a little bit more useful. Okay, let's talk about collisions really briefly, because we're going to do the problem when it's a collision. If I have a collision between two objects, they're in contact. So this is object A, and this is B. So there's a force FB on A, and there's a force FA on B. But according to Newton's third law, those two forces are equal and opposite, so they have the same magnitude. And if that's the only force acting on it, that force FBA is going to be the change in momentum of A. So I can say FBA, that's the only force, is delta PA, delta T, that's a vector. And then I can do the same thing, FAB is delta PB delta T. But if these two forces are equal and opposite and the times are the same, they have to be the same. Then the change in momentum of B has to be equal and opposite the change in momentum of A. So I can say delta PA minus delta PB is 0. Zero vector. Remember, I've talked about the zero vector. Okay. So if the change in momentum of the thing is 0, or then the change in momentum of these two would be equal, no, this is plus, right? Because this is equal to the negative of that. So those two added together. So if the change in momentum is 0, one way we can write that is P total initial is P total final. And that's what we call conservation momentum. But remember that that only works if there's no other external forces. If there's an extra force right here, then the net force on A is not equal and opposite to the net force on B, because they'd have different forces. Finally, we have another criteria. We have this thing called an elastic collision. And it turns out in an elastic collision, not only is momentum conserved, but kinetic energy is conserved. So the kinetic energy total initial is equal to the kinetic energy total final. That's that. Now, if there's no external collision forces, momentum is conserved. If there's also the special condition, then kinetic energy is conserved. There's also a inelastic collision, where the two things stick together and they have the same velocity. But momentum's still conserved. Okay. You ready to do the problem? I'm ready. You know, and I know I fly through that stuff, right? Because I could spend an hour lecturing and deriving things, and I have done that. That is true. But in this little haiku physics I made up, I'm just trying to solve the problem and use that to explain the physics. So maybe it's useful. Maybe it's not. Maybe we'll just have fun. I'm having fun. Okay. So let's get back over here to the problem. I have a pool ball, initial velocity collides with the ball, and then I have this glancing blow. So what do we know is true? If there's no external forces, then I know the momentum is conserved. The momentum is constant. Now there's a couple ways we could write this. I'm going to write it out as a vector first. Okay, because I know that I can write this. P total initial is P total final. I just derived that. Do you not remember? I just derived that. Well, let's just write down the initial momentum as a vector. Well, initially, before the collision, I have this mass moving, and that one's not. It's at rest. So I can write down the following. M, and I'm going to use their notation, v1I for the initial velocity, plus m, the mass of the other one, times 0, just writing it out the full way. And that's going to be equal to m v1 final plus m v2 final. So that's the situation I'm working on, right? I know that value. I kind of know this. I know that velocity because they give me the magnitude and the angle. But I do indeed know that. And then I'm trying to find that velocity. So there's a couple things we can do. We could either write these as vectors, which is, I don't think that's what they want you to do, or we could write this vector equation as two scalar equations, right? Because if it's a scalar, if it's a vector equation, the x components of this side have to be equal to the x components of that side. The y components of this side has to be the y components of that side. So the first thing I'm going to do is to divide both sides by the mass. Since they have the same mass, that cancels. Now let's write down the x component. So v1ix plus 0 is equal to v1fx plus v2fx. And then I have the y, v1iy is v1fyy plus v2fy. Okay, so we're going to have a bunch of things in here that are simpler, right? Let's just sketch out our picture right there. So I want to get the x velocity of this. So here's my ball moving that way, and here's the angle theta 2, v2f. They give us that magnitude. So I can find the x component and the y component with that right triangle. So if I know the hypotenuse of that, which is 1.1, and I know the angle, then I know this x component is going to be v2f cosine theta 2. And I'm just going to write that in there, okay? So up in here, I can rewrite my equation. v1ix only has x velocity, so it has no y component. So this is just going to be equal to v1i times cosine of 0, which is 1, plus 0. And this is going to be v1fx. I'm going to leave it like that, plus v2f cosine theta 2. Now, I know theta 2, I know v2f, I know vi, so I can find this value. Let's just go ahead and find that. v1fx is going to be v1i, 1i, minus v2f cosine theta 2. I'm going to put in my numbers. This was 2.2 right there. This is minus 1.1 cosine of 60. So let's put that in our calculator right here. Okay, on, drop, 2.2, enter, 1.1, enter, 60 cosine times, minus, and I get 1.65. Now I need to do the y direction. So in the y direction, I'm going to write it right here. I know my initial y velocity is 0. I don't know my y final there, and I do know here. So over here, v2 v2fy is going to be v2f sine of theta 2, right? Because that's the opposite side. So if I put that in right here, I'm going to just put it in as numbers. I have 0, well, not numbers, equals v1if. And then that one's in the positive x direction. You do have to look at whether it's in the positive or negative. That one's in the negative x direction, but I'm just going to solve for that. That's in the positive x direction, so it's going to be plus v2f sine theta 2. So if I solve for that, I get v1 fy is negative v2f sine of theta 2. So it's going to be negative 1.1 sine of 60. Calculator time. 1.1 enter 60 sine times. So I get negative 0.952 meters per second. So I have that one and that one. Now, the question asked, what's the angle and the magnitude? So we're going to have to find that. Let's go ahead and just go backwards and draw a picture. So here's my final velocity. I know it goes like that. I know the x component, v1 fx. I know the y component, v1 fy, and that's theta 1, and this is v1 f, the final velocity. So I know that those two components, so I can find the magnitude. v1f is going to be the square root of v1fx squared plus v1fy squared. So I'm going to use these two numbers, square them, add them together, take the square root. Let's do it. Glasses off because I can't see that. Oh, I dropped. Why did I do that? Okay. 1.65 squared. That one. Not negative, but who cares? 0.952 squared plus square root. So I get a final velocity of 1.90 meters per second. Now for the angle right there, they describe that below the x-axis. So you have to be careful when you find these angles because they're ambiguous in a certain degree. So let's just use, we know it's already below the axis, the way they drew it. I'm going to just use the tangent. I'm going to say tangent of theta 1 is equal to v1, that's a y, v1 fy divided by v1 fx. And then so the inverse tangent of that would be my angle. So I have, let's just do that, drop. I have v1 fy is opposite or adjacent. That's right? Yeah. Okay. So that's 0.9, I'm not doing negative, 0.952, 1.65 divided by, and then inverse tangent. And I get theta 1 is equal to 30 degrees. So over here, I can go ahead and put in my answers. I have 1.9, 30 degrees. One of the things you'll notice, and this is something that's true for, I think it's definitely true for elastic collisions. It can't be true for inelastic collisions because I can imagine one where they stick together. The angle between these two recoiling things is 90 degrees. So that's 60, that's 30, that's 90 degrees. So I'm pretty sure it's an elastic collision. But let's go ahead and calculate and see if it's an elastic collision because that's the last part right there. It's elastic if the kinetic energy before and the kinetic energy afterwards are equal. Now remember, kinetic energy is a scalar value. It's not a vector. I always have students try to do something like that. So K total initial, is it equal to K total, that's a weird one, final. So K total initial is going to be equal to 1/2 m, which we don't know, and that's fine, times V1 initial squared. So that's the magnitude of it squared. K total final is going to be 1/2 m V2 final squared plus 1/2 m V1 final squared. So I know that. I don't know the mass, but I'm trying to see if these two things are the same. So I can divide both sides by the mass, and they'll still be the same, and then I don't have to worry about that. Okay, so let's just get kinetic energy over the mass for that first one. I know my initial velocity was 2.2, and I don't even need the 1/2, right? So let's do this. 2, 2. I mean, why do extra work if we don't have to? So I'm going to take 2.2, enter square it, and I get 4.84. Now down here, I'm going to take my final velocity of 1.1 squared, and then I'm going to take that other one of 1.9 squared, and then I add them together. And I get 4.82. And it's not actually joules, but it's kind of like joules. And I think those are the same. I think kinetic energy is conserved. You have to be careful because I rounded, and when you round and then square, and when you round and you take the square roots, the rounding becomes more noticeable. But I'm pretty sure this is an elastic collision, again, because of that angle being 90 degrees, which I should derive at some point, and it would be kind of fun. But not here, because it's 24 questions. I can only do 24 questions. I can't make up new problems. I will say in the book there was the ballistic pendulum. I think that's a great problem that involves both energy and momentum. It's kind of cool. But again, I'm sticking to one problem per chapter for most chapters, not all chapters. 24 questions, number 8, playlist down below. You know, was that 8? Yeah, number 8, yeah, 9 comes next.